Okay, so let's begin with this question. Okay, so first of all, if we just relate the given function with respect to our concept of the general equation of traveling wave, we can see the argument of the function is linear in x and t. So we can see it represents a traveling wave. Secondly, we can see that the function is periodic because we know sine square function is periodic. So not only it represents a transverse wave, but it represents which type of transverse wave, a periodic or a continuous transverse wave, which means that the medium has a certain wavelength and the particles in oscillation have a certain time period. Now the question is of calculating that, and that is where the snapshot picture comes in. Okay. So let's start with the first thing. So given this function y is equal to 8 sine square pi by 6x minus 20 pi t, where y was in millimeters, x in meters, and t in seconds. So we can observe that this is a function of this time, where f is the sine square function. Okay. So it is a periodic function, which means that y represents a periodic or continuous graph. Transverse wave. We can also see that in addition to that, the value of k is pi by 6 radians per meter. The value of omega is 20 pi radians per second. So eventually I'll tell you a trick by which we can calculate the wavelength and time period directly. Okay. So here we will actually see that the wavelength is 6 meters and the time period is 1 by 20th of a second, okay, or 50 milliseconds. But let's understand this in more detail. Okay. So now the first part, let us look at y at t equal to 0 as a function of x. What is that becoming? That is becoming 8 sine square pi by 6x. So it's a sine square type of graph. So we know that y is equal to sine square theta. This thing as a graph varies between 0 and 1. So we will make use of that while plotting our particular graph. So theta this kind of thing varies between 0 and 1. So here let us understand how this particular graph will look like now. So this particular graph is like this. Now you can see that at this point y will reach a value of 8 millimeters, whereas x in meters will be such that at this point the value of theta, which is kx, pi by 6x is the theta. So when theta is pi by 2, what about x? It should be 3 meters. When theta is pi, x should be 6 meters. When theta is 3 pi by 2, x should be 9 meters. When theta is 2 pi, x should be 12, and so on. So from this graph, you can see that what is the wavelength? It is this periodicity, okay, or that is this periodicity. So you can see according to the graph, the value of lambda should come out to be 6 meters. So note that it is 6 meters and not 3 meters because it's the sine square function and not the sine function. Okay. Now the same thing, if you want to understand how this graph looks, or we want to understand the snapshot picture at 1/40th of a second, okay, or 25 milliseconds, or at 50 milliseconds, that is 1/20th of a second. So let's understand that also now. So at t equal to 25 milliseconds, this will become 8 sine square pi by 6x minus 20 pi into 25 into 10 raised power minus 3. So this factor, this omega t term, 20 pi into 25 into 10 raised power minus 3. So that is 500 into 10 raised power minus 3 pi. So it's pi by 2. Okay, so this actually becomes 8 sine square pi by 6x minus pi by 2. So that is the same thing as 8 cos square pi by 6x. So this is how the graph of y versus x looks like at t equal to 25 milliseconds. So now if I just superimpose this snapshot picture on the first one, so you see now it looks like this. This is what it looks like at t equal to 25 milliseconds. Whereas this is what it was looking like at t equal to 0. So you can see that these are all shifting like this. Wave is shifting at a certain speed. You can see each of the peaks, they've shifted by 3 meters in a matter of 25 milliseconds. Okay. So this is also showing you that your wave speed should be equal to 3 meters every 25 milliseconds. So that should be 3 into 10 raised power or 1000 divided by 25. It's apparently 1200. Oh, sorry, 120 meters per second. That should be our wave speed. Okay. Now, next thing, if you look at t equal to 50 milliseconds or 1/20th of a second, y will become 8 sine square pi by 6x minus 20 pi into 50 into 10 raised power minus 3. You see that this term becomes pi. So it becomes 8 sine square pi by 6x minus pi, which is the same thing as 8 sine square pi by 6x. Because sine square function has a periodicity of pi. You know this, that sine square of pi plus theta is sine theta. So you're making use of that. So now you can understand what's happening in terms of the graph. The graph is shifting in such a way that it was like this, let's say, at t equal to 0. Then by the time you came to 25 milliseconds, this peak shifted here, and this stuff shifted here like this. So it became something like this. Oh, sorry. So all these shifted by 3 meters we saw in 25 milliseconds. Now in this one you will see it's back to the original graph, which means that these have all shifted. Oh sorry, it's the sine square graph, my mistake. Just a minute, people. I have to redraw the thing. Right, so coming back here. This was the shape at t equal to 0, where we saw that this was 3 meters. So therefore this became 9. This became 15. Like this. Now, by the time we came to 25 milliseconds, we saw that this whole thing has shifted like this. Okay. So each of these peaks you can see have shifted by a distance of 3 meters in 25 milliseconds. Now, by the time we are coming to 50 milliseconds, you will see that it's back to the original graph, which means that it's something like this. Again, you are back to this graph, which means that actually this peak has shifted here. This peak has shifted here. So it's repeating the graph, but actually the whole pattern has shifted. And that's how we are getting this. So again, it has shifted 3 meters in 25 milliseconds. Okay? So it is showing you that it is repeating itself once every 50 milliseconds. That is what this graph is also showing us, the superposition of these graphs. So we can see from this that not only we can understand that the wavelength is equal to 6 meters, you can also see that the graph repeats every 50 milliseconds. So according to this, the time period should be 50 milliseconds, or the frequency should be 1 upon time period, so 1000 upon 50, so it should be 20 hertz. Now we'll also understand this from the graph of the oscillation, y as a function of time. Okay, but first make a note of all these. Okay, so next up, let's come to this part where we are plotting y versus t. Okay, this second part. We're done with this part. So let's do this now. Let's plot y as a function of time for the particle or the point which is x equal to 2 meters on the medium. And now analyzing all these things, we'll be able to calculate the parameters amplitude, wavelength, time period, etc. Okay, so we plot the graph of this particular point x equal to 2, the graph of y versus t. So we are plotting the oscillation equation for it basically. So pi by 6 into 2 minus 20 pi t. Okay, so this is the equation for the motion of the point x equal to 2. So you can see that this becomes basically, so sine square. So this becomes 8 sine square 20 pi t minus pi by 3. Here I've just used the trick that sine square theta minus omega t will be the same thing as sine square omega t minus theta, because sine square theta is the same thing as sine square minus theta. Okay. So using that, we'll see how this graph now basically looks. So y in millimeters versus time in seconds. You see at t equal to 0, its value is sine square of minus pi by 3. So that is sine square pi by 3 or root 3 by 2 ka whole square into 8. which value is 3/4 of 8. So it's 6, something like that. So 3/4 is, let's say, something like this. The graph is going to go something like this. This is how it's varying with time. Oh, sorry, it comes down, it doesn't go up. Okay, because this thing reduces to 0 first now. So it initially comes down. Then so this will be 6, this will be 8 millimeters. Now this time, what will this time be? Suppose this is T1, this is T2, this is T3, this is T4. So let's calculate these values of time. So you can see that at T1, sine square 20 pi T1 minus pi by 3 is equal to 0 for the first time. So that means 20 pi T1 minus pi by 3 must be equal to 0. So that means T1 must be pi by 3 into 20 pi. So it must be 1 by 60th of a second. So T1 must be 1/60th of a second. Now similarly at T2 you can see sine square 20 pi T2 minus pi by 3 is becoming 1 for the first time. That means 20 pi T2 minus pi by 3 is equal to pi by 2 for the first time. Okay. So that means you will see you get your T2 as this will become pi by 2 plus pi by 3, so that's 5 pi by 6 divided by 20 pi. So you will get this as 1/24th of a second. So T2 will come out to be 1/24th of a second. And similarly T3, when you calculate at T3, this sine square omega t minus pi by 3 kind of term is 0 again. So that means that omega t minus pi by 3 term this time is becoming pi. So from that, when you calculate T3, you will see you will get that as it as 4 pi by 3 divided by 20 pi. So you get that as 1/15th of a second. This kind of thing. So these are the various values of time we get. Now you can see that in this graph, the time period according to this graph should be this one, or that is the same thing as this one. Let's see what we get from these values. So the time period which is T3 minus T1 or T4 minus T2, any of these, 1/15th minus 1/60th, so 1/20th of a second, okay, or 50 milliseconds. And that is what we had seen earlier also from the superposition of the snapshot pictures. Also we had surmised the same thing. But here we are getting it in a more proper manner by looking at the oscillation of a particular medium particle. Okay. So this graph is showing you the oscillation of a particular medium particle as a function of time. that oscillation is showing you that it is oscillating between 0 and 8 millimeters. So that means the amplitude of oscillation is equal to 4 millimeters, because amplitude is always equal to maximum value minus minimum value, that range ka half. It is like while this oscillation is happening, this 4 meters position, 4 millimeters position, this is the mean position, and this is one amplitude, or this is one amplitude. That's why if the function is a sine square or a cos square kind of function, instead of a sine or a cos function, you have to be a little extra careful. And time period we just saw as 50 milliseconds, or 1/20th of a second. Yeah, Aditya. So what is happening? See, ये जो particles का oscillation हो रहा है, इसमें y का minimum value कितना है? 0 है ना? It's not going to a negative value of y. It's just going between y equal to 0 and y equal to 8. So oscillation के जो extreme positions है, वो कितना है? 0 and 8. That means mean position is always the midpoint of the extreme positions. No? So mean position is equal to x equal to 4 millimeters, and amplitude. So this thing, it's showing you that y का minimum value 0 है और y का maximum value 8 है. So therefore mean position is 4 millimeters and amplitude is equal to also 4 millimeters. Is it clear, Aditya? In any oscillation, suppose the oscillation was happening between -2 and 6. So again, the range of oscillation is 8 millimeters. So the amplitude would be how much? It would be 4 millimeters. But this time the mean position would be +2, because it is going between -2 and +6. Similarly, here it is going between 0 and 8. So mean position कितना है? Y equal to 4 mean position है, और amplitude कितना है? 4. So it is going between 4 + 4 and 4 - 4. Okay, yeah. So always the range of motion is double of the amplitude. Extreme to extreme, double of amplitude. So this is something important both from the perspective of SHM and oscillations, as well as in perspective of waves. Okay, so now coming to the final part, I just give it a bit of time to note down this thing. Okay. Now notice this 50 milliseconds time that we are getting by actually just analyzing the time period of the oscillation graph, we had earlier also got it by our work on this graph, okay, where we compared the snapshot pictures at various different times, and we saw that from 0 to 25 the graph is shifting from sine square to cos square, but then from 25 to 50 again it's going from cos square to sine square. So the whole graph is repeating itself every 50 milliseconds. So here also we had understood from a different method altogether that the time period was 50 milliseconds. Here we are getting from a different thing. From the plot of y versus t, we are getting the time period as 50 milliseconds. So it confirms the same thing. So now we will just put together all this information. So we can see that therefore, okay, the given wave, or what we call a periodic transverse wave, has amplitude equal to 4 millimeters, okay, wavelength equal to 6 meters, time period equal to 50 milliseconds, or frequency equal to what we saw 20 hertz. Okay. And also it has a wave speed which we had calculated above was 120 meters per second. Okay, now we can see something interesting here, that this wave speed that you're getting, you can calculate it in many ways. Like it is f lambda, so it's 20 hertz multiplied by 6 meters or 120 meters per second. Or you can also use the formula that it is omega by k. So omega was 20 pi radians per second and k was pi by 6 radians per meter. So from that also you can see you are getting 120 meters per second. Whereas we had interpreted it from the graph also. Okay. So we have this relation B is equal to omega by k, which is equal to f lambda. Now we'll understand very soon why omega by k is equal to f lambda, because there's a certain relationship between these terms. So just make a note of this point here first. Because our original function was this one. Our original equation was 8 sine square pi by 6x minus 20 pi t. Okay. So the amplitude became half of this, because y is ranging not between -8 and +8, but it's ranging between 0 and 8. Okay. But this term is still k. But now notice something interesting. What is the relation between k and lambda, and what is the relation between k and omega? So that's the next thing you'll understand. About wavelength lambda and frequency f. So in any given equation, if f is a periodic function, okay, with fundamental period, okay, from graphs and functions in maths, you understand what is a fundamental period, with a fundamental period of t, okay, then okay, lambda becomes that fundamental period divided by t, and time period becomes that fundamental period divided by omega. Or this is the same thing as saying that frequency is omega by that fundamental period. So before you note this down, let's observe this with an example. So for example, if we had the function y equal to 8 sine square pi by 6 x minus 20 pi t. Now this function is which one? This function is sine square theta type of function. So it has a fundamental period of how much? Pi. Sine square theta repeats itself every pi. That we had seen earlier. Repeats itself every pi. So this is the fundamental period, or this here is the fundamental period. So if the fundamental period is pi, you can see that k, which is pi by 6, is nothing but fundamental period divided by lambda. So pi by 6 is equal to pi by lambda, or lambda is equal to 6 meters. Okay. And you can also see that here omega was 20 pi. Now that should be equal to p by time period. Okay. So 20 pi should be equal to the fundamental period, which is pi, divided by time period. So your time period is 1/20th of a second, or 50 milliseconds, or your frequency is 20 hertz. Okay. So this is all coming from the fact that the sine square function has a fundamental period of pi. So once we know these formulae, then things like frequency and all, we don't need to plot the graphs. We can directly use this formula. So for sine square and cos square function, the fundamental period is, okay, so that's what we understand here. For this function being sine square or cos square, okay, the fundamental period is pi. So your lambda will become pi by k, and omega will become pi by time period, or pi f will be equal to omega, where f is the frequency. And further, one more thing, v is equal to omega by k. So that is nothing but fundamental period divided into frequency divided by fundamental period divided by lambda. So that's how we get the relation that v is equal to f lambda. So whatever type of periodic function it is, whatever the value of capital P, the fundamental period is, when we say v is equal to omega by k, the wave speed equals to omega by k, that is exactly the same thing as saying that it is frequency into wavelength, or that it is saying it is wavelength divided by time period. So these two relations are exactly the same as this relation. So it doesn't make any difference how we interpret it. Okay, so people hope you've understood this thing. So I'll just take you above once and then you come to this example. Okay, so about wavelength and frequency, how we interpret it directly in terms of the mathematical function without plotting the graph and all that. The moment that function is periodic, don't confuse between the f used for function above over here and f used below for frequency. They are different things. Okay? F used in the first two lines are for the function. Now the moment that function, which is linear in x and t, is periodic, we know that the wave has a wavelength and it has a time period because the medium particles are oscillating. So how will we calculate that wavelength and time period? By using the simple relation that lambda will be fundamental period divided by k, where k is the coefficient of x, and time period will be that same fundamental period of the function divided by omega, where omega is nothing but the coefficient of time. Okay, people, hope this is clear to all of you. Okay, so this is clear, people. So these formulae become important. Okay, that how we calculate. For example, in the case of sine square and cos square, that fundamental period is pi. So lambda becomes that fundamental period divided by k, and omega becomes that fundamental period divided by time. Okay, next up, two more important properties from a given wave equation. You'll understand is particle velocity, which we denote with a different symbol Vp, and particle acceleration, so that we don't confuse these with the wave velocity. And the wave is of course traveling at a constant velocity, so it does not have acceleration. So what happens is in a transverse wave, while energy is propagating along the length of the medium, in this case the string, so that is along x-axis, the medium particles themselves are not displacing along them. They are moving along the transverse direction, which is nothing but the y-axis. Okay. So the instantaneous velocity of any medium particle along that y-axis at any point of time, the instantaneous velocity of any medium particle at x equal to x at time t equal to t. So x is like the address of that particle or the x coordinate of that particle, but it's moving along which direction. So that instantaneous velocity of this particle is along the y-axis. So what is happening? Y as a function of kx plus or minus omega t. What does the y represent? It represents the displacement. This represents the instantaneous displacement, okay, of the particle x equal to x at time t equal to t. So therefore, what should be the particle velocity? It should be the rate of change of displacement. So particle velocity should become the rate of change of displacement for that particular value of x. That means we have to find rate of change of y with respect to t, keeping the value of x as constant. So that means nothing but it is partial gradient or partial differentiation of y with respect to time. So it is del by del t of this function kx plus minus omega t's function. So next we apply partial differentiation here. So you can see that the particle velocity, which is the same thing as del y by del t, becomes plus or minus, depending on whether this sign is plus or minus, omega into derivative of this function kx plus minus omega. So this is how we find the particle velocity. And similarly, particle acceleration, okay, EP, this will be again instantaneous acceleration of x equal to x at time t equal to t along the transverse axis. The motion is happening along the transverse direction. So this acceleration will be del Vp by del t, which is the same thing as second derivative of y with respect to t, but partial derivative, keeping this thing constant. So just now we saw this was plus minus omega f prime of kx plus minus omega t. Okay. So ये वाले पूरे function का, that is this whole thing's partial derivative with respect to time, because that thing is your Vp. Okay. So our particle acceleration, which conceptually is second partial derivative of y with respect to time, formula wise you can see now this plus minus omega outside gets multiplied with another plus minus omega when you differentiate one more time. So that takes the sign away. So it just becomes omega square f second derivative of kx plus or minus omega t. When you differentiate this one more time by your chain rule, plus minus omega comes out once more. So plus minus omega multiplied by plus minus omega, the sign of that plus or minus omega t goes away. It's just omega square into this. So this becomes the formula for particle acceleration. So there can be a direct question based on this also. Given a wave equation, you have to find the particle velocity and acceleration for a particular point. So there, don't confuse the particle velocity with the wave velocity. Now, the transverse wave's own velocity, propagation velocity, that is your f lambda or omega by q, and its direction is positive x-axis or negative x-axis depending on the sign of omega t in the equation. But particle velocity and particle acceleration are different things. They are the rate of change of displacement or velocity of the motion of the particle along the y-axis. So that's why they are del y by del t, and second derivative of y with respect to t partially. Okay, so just make a note of this, people. This is another important concept related to the general equation of wave. Okay, people. So hope this is clear. So let's look at a quick example. So here y is in centimeters, x is in meters, t is in seconds. So the first thing is that does the above equation represent a transverse wave? Okay. If so, is it periodic or not? Okay. Then find the maximum y for any x at any time. Third, plot the snapshot of y versus x at p equal to 0.2 seconds and find the particle velocity and particle acceleration of the particle at x equal to 0 at the instant t equal to 0.2 seconds. So at this moment of 0.2 seconds, what is the particle velocity and particle acceleration of the particle which is at the origin? Okay, so this question should clear up all aspects of what we just discussed about particle velocity and particle acceleration. Also, it's giving you a quick recap of the concept of exponential pulse. Okay. So you can compare it with one of the questions we did last time also about the exponential pulse, and you can see you get the answer accordingly. Okay, so we can see that first of all, the answer to this is yes, because y is a function of kx minus omega t, where that function is e raised power minus theta square, and that argument of the function is 5x minus 2t. Okay, but the function is non-periodic, so the answer to this is no. Okay, because the function is non-periodic. Okay. And the propagation speed v is omega by k, which will be 2 by 5 meters per second or 0.4 meters per second. So from all this information, we can again see that y being 4 into e raised power minus of 5x minus 2t whole square. You can see that y's maximum value is equal to 4. That's the second part's answer, because e raised power minus theta square's maximum is equal to 1 for theta equal to 0. And e raised power minus theta square's minimum value is tending to 0 as theta tends to plus or minus infinity. Okay. So now you can see that at t equal to 0.2 seconds, y is becoming 4 e raised power minus of 5x minus 0.4 whole square. Whereas, for example, if you compare this with y at t equal to 0, that is 4 into e raised power minus 5x whole square. So the graph of y versus time will be like this. It will be an exponential pulse such that, for example, at t equal to 0, the pulse would have been peaking here. This is how the pulse looks at t equal to 0. Its peak value is 4, which is occurring at x equal to 0. But now, for example, at the designated time where we have to calculate, it's peaking at, so at t equal to 0.2 seconds, you can see y is equal to y max or 4 at the position where 5x minus 0.4 becomes 0, or x becomes 0.4 by 5, or x becomes 0.08 meters. So this peak would have shifted to this position 0.08 meters at t equal to 0.2 seconds. So this is also showing you the story that the speed by this calculation is 0.08 meters in 0.2 seconds. So it is 0.4 meters per second, which is also, by the way, equal to omega by k, because this was the original equation. Okay, so now let us come to the particle velocity and particle acceleration part. Okay. So we want to find the particle velocity and particle acceleration for the point x equal to 0 at the instant of time t equal to what was it, 0.2 seconds. Okay. So we had this function this, okay, where a we saw was 4 centimeters in this case. Okay. K was 5 meters inverse, okay, and omega was 2-second inverse. That was this function. So the particle velocity, which is del y by del t, is partial differentiation of this function. This function, okay. So in this function, partial differentiation means क्या करेंगे हम इसको t के respect में differentiate करेंगे, treating a like a constant. Okay, so treating x like a constant will differentiate with respect to time. So exponential functions differentiation is exponential only. Okay. Multiplied by differentiation of this whole term with respect to time. So minus 2 into kx minus omega t, okay, into differentiation of this with respect to time, so minus omega. So we get the formula of particle velocity as 2 times a omega e raised power minus kx minus omega t the whole square. Sorry, there is one more term. Let's come into that just a second. There's also the linear term. So that particle velocity formula will become 2 times a omega into this linear term kx minus omega t, okay, into that exponential term. So this becomes a particle velocity in general. So now in this we have to substitute, first of all, in our case here, this is 4 centimeters and omega was 2-second inverse. So this factor becomes this. Then kx minus omega t becomes 5x minus 2t into e raised power minus of 5x minus 2t whole square. So now for our particular case, we are looking at x equal to 0 at t equal to 0.2 seconds. So this will become 16 into 0 minus 0.4 into e raised power 0 minus 0.4 whole square. And this unit will be centimeters per second. So the particle velocity of that point will become minus 6.4 into e raised power minus 0.16 centimeters per second. And the minus sign is showing you that the particle at the origin will be coming down. I'll show you why that is the case. Okay. So this is the particle velocity at x equal to 0, t equal to 0.2 seconds. Now we'll understand why this minus sign before you note this down. Okay. So note, the negative sign indicates that the particle at x equal to 0 is coming down, or Vp is along negative y-axis, okay, at t equal to 0. Now let's understand why that's the case. Because if you remember the snapshot picture we had drawn, at that instant, it seemed the snapshot picture would have been something like this. This is at the instant 0.2 seconds. So the peak was occurring at 0.08 meters, and that peak's value was 4 centimeters. So anyway, the particle at the origin was over here at that instant. So the particle at the origin was here. It was located over here. Now, as we shift time by some small amount delta t, let's say, what will happen is this will shift by a small amount in this direction. This is how this peak will look at t equal to 0.2 plus some delta t, where delta t is a small amount of time. Now, because we know that this is traveling along the positive x direction, so we can see that this particle will have a particle velocity which is in the downward direction. So that is also showing why Vp came out to be a negative quantity. The del y by del t at x equal to 0, t equal to 0.2, it came out to be a negative quantity because of this physical reason. As that pulse is shifting, the shape is shifting along the x-axis, but the medium particles, they are only either moving up or moving down. They are not moving along the x-axis. They are moving along the y-axis only. So that's the reason why this happens. So just make a note of this point, this concept here. Okay, now we see the particle acceleration over here. So this is clear so far. It's a little bit one step more complicated than this, because we now have to differentiate this term. This whole term will have to be differentiated. So the particle velocity, the particle acceleration rather, which is del 2y by del t square, it's over here going to be del by del t of the particle velocity. So it's going to be partial differentiation with respect to time of this function, 2a omega into kx minus omega t into e raised power minus of kx minus omega t whole square. So we're going to have to apply the product rule now. So as you can see, 2a omega will come outside, and then we are left with differentiation of this term, that's minus omega, into the second term, so minus kx minus omega t whole square, plus this term only, plus kx minus omega t into differentiation of that exponential function, which we had seen just now. So we don't need to repeat that whole thing. Differentiation of that exponential function is e raised power minus of kx minus omega t whole square into 2 times minus of kx minus omega t into minus omega, this whole term. So this will become 2a omega e raised power minus kx minus omega t whole square. We can take common. So this term gives us minus omega, and this term gives us 2 times omega into kx minus omega t whole square into that we wanted it. Okay, so we can in fact write this as 2 times a omega square into 2 times kx minus omega t whole square minus 1 into this factor. ये मेरा particle acceleration का equation है. So now you can see that for our given function here, it will become 2 times amplitude, which was 4 centimeters, into omega, which was 2 second inverse का whole square, okay, into 2 times 5x minus 2t whole square minus 1 into e raised power minus of 5x minus 2t whole square. So now we can substitute the values and get this over here. So acceleration of the particle at x equal to 0, t equal to 0.2 seconds. That will become 4 to the 8 to the 32 centimeter per second square. Okay. This thing into 2 times minus 0.2 whole square, because this term is 0, okay, minus 1, okay, into e raised power minus 0.2 whole square. So is this very odd kind of number, but importantly this is the concept. Okay, this is how we calculate it. So you'll see that acceleration of that particle will become minus 32 into this factor will become 1 minus 0.04 into 2, so 0.08, okay, into e raised power minus 0.04. Oh, sorry, this was 2t, so my mistake. This is a different value. This is 2 into 0.2, no? Because we are taking the time as 0.2. So this is, this and this are both different values. Okay, this is it. So this value here is 0.4. 0 minus 2 into 0.2, so that's 0.4. And this is also 0.4. So this will become 0.16 into 2, so 0.32. And this will be 0.16 in centimeters per second square. So let's see this acceleration. So this is the acceleration. And again, the fact that the sign is negative means that the acceleration vector points downwards. So negative sign means that the acceleration vector is pointing downwards. So the particle was already moving downwards, so it's also accelerating downwards. That means its speed is increasing as it's coming down. Okay, so this is an example of how we calculate the particle acceleration. Okay, so that is about particle velocity and particle acceleration. So with this discussion, actually, we complete the part where we understood the general equation of transverse waves and the significance of the various quantities in the general equation. Now we come to the more specific part of understanding what is called sinusoidal or harmonic this thing, transverse waves. Okay. So sinusoidal, or these can also be called harmonic transverse one-dimensional waves. So this is just a case where that function is nothing but the sine function. So the general equation of this becomes y is equal to some amplitude into sine kx plus or minus omega t plus some phase constant phi. So this is your function of kx plus or minus omega. So this represents that harmonic wave with, now importantly, amplitude becomes nothing but a over here, because y is maximized plus 1 and minus minus 1. So amplitude is a, because you can see that y is oscillating between plus a, the position is 0 for any point. It is oscillating between minus a and plus a. So mean position, unlike that sine square function we had seen, the mean is 0, not a by 2. So that's why the amplitude is a. Okay. Wavelength lambda equal to 2 pi by k. because again the fundamental period is how much? 2 pi for sine function. So 2 pi by k becomes the same time period. Two pi by omega, or frequency equal to omega by 2 pi, because of this reason. And propagation speed p equal to omega by k equal to f. So note kx plus omega t plus pi being the argument implies that the propagation speed is along negative x-axis, and kx minus omega t plus pi being the argument implies that v is along positive x-axis. And this reason you understood before is to do with the transformation concept. So you just understand this as a special case of the general equation of transverse wave that we have understood. But since this is the most important type of wave motion for us, okay, so at this stage we are going to pay special attention to these values and the properties of this particular function, and all the analysis that we are going to do from this point onwards, like understanding the power transmitted by a wave and the relationship between the wave speed and the medium properties, etc. And then eventually superposition of waves to understand things like interference and standing waves, etc. All that analysis will be taking into account the general equation of sinusoidal or harmonic wave. So from this point in this chapter, our analysis for waves will shift from the general type of equation to the general harmonic type of equation, or the general sinusoidal type of equation. Okay, people. So let's understand this with an example now. Now, before that, the significance of the phase constant phi. Let's also understand that. So, also the quantity k being 2 pi by lambda, it is for this kind of wave, it is called the angular wave number. Okay. Because 1 by lambda is wave number. So we can think of it as number of wavelengths per unit length. For example, if I take lambda as 20 centimeters, So 1 by lambda is 1 meter divided by 20, so it's 5. So it's that wave number, the number of wavelengths that fit in 1 meter. So that's why K, which is 2 pi into 1 by lambda, that is now called angular wave number. So you should know the term angular wave number. Similarly, the term omega, which is 2 pi f or 2 pi upon time period, it is called angular frequency, because omega is 2 pi multiplied by frequency. So angular wave number and angular frequency, these are these two terms. You should understand this also. So make a quick note of this. Okay. Now additionally, the term phi over there is called the phase constant. It is such that if you look at y at x equal to 0, t equal to 0, it is nothing but a sin phi, because y as a function of xt was this, and particle velocity at x equal to 0, t equal to 0 is nothing but e omega or plus minus e omega cos phi, because from this you can see that particle velocity, which is del y by del t, is plus minus e omega cos kx plus minus omega t plus phi. So that is the significance of the phase constant, that y at x equal to 0, t equal to 0 is given by a sin phi, and particle velocity at x equal to 0, t equal to 0 is given by plus or minus of e omega cos phi, depending on whether this sign is plus or minus. So just like in SHM, the significance of the phase constant is to do with initial position x naught and the initial velocity v naught. So here also the significance of the phase constant or initial phase is to do with that. Okay, so let us understand all this with an example. So x is in meters, p is in seconds, and y is in millimeters. So first thing is find the amplitude, wavelength, lambda, and time period capital. Not the snapshot. Find velocity and acceleration at x equal to 4 meters, t equal to 0, 1/40th of a second. So just try this out, people. So basing on a couple of questions on this. We've done one like this last time also. Okay, so you can directly see what the amplitude and all that is. Just compare this equation with the standard equation. This is traveling along the positive x-axis because the sign between omega and k, omega t and kx is negative, so you can see. So amplitude is equal to 10 millimeters. Okay. Because y is given in millimeters. K, which is pi by 8, is equal to 2 pi by lambda. So the wavelength is equal to 16 centimeters. So 16 meters. X is given in meters. Because this is in radians per meter, because x is in meters. Okay. And similarly, omega is 40 pi in radians per second is 2 pi f. So the frequency is 20 hertz, or the time period is 50 milliseconds, or 1/20th of a second. So these are all these basic things. And you can see that the propagation velocity is f lambda or omega by k. So that is becoming 320 meters per second along positive x axis. That is the wave propagation velocity. So that's about these things. Now the snapshot at t equal to 0. So for the snapshot, first of all, write the formula for y is a function of x at t equal to 0. So it is 10 sine pi by 8x plus whatever that phase constant was, pi by 6. So all we have to do is plot this graph. Now this is where practice comes in very handy of plotting such type of graphs. So you know that if you were plotting y equal to sine theta, it's a very standard graph. So should be well practiced and you should know that that graph looks like this. Just like you did for SHM graphs. So 0, pi by 2, pi, 3 pi by 2, 2 pi, etc. Varies between 1 and minus 1. Now, if I transform this to sine of theta plus pi by 6, तो क्या होगा? ये ग्राफ लेफ्ट की तरफ शिफ्ट हो जाएगा by pi by 6. So pi by 6 पे, you know, 30 degrees पे pi by 6, the value of this becomes half. So it shifts pi by 6 this way. So how this graph looks now? This one looks like this. Compared to the earlier one, you can see it shifted this pi by 6 in this way. So the value is half at 0, and at pi by 3 it reaches the peak. Okay. So now we are going to plot this only, but replace the value of theta with what? Pi by 8x. So accordingly, our data points will shift. So this graph is going to look like this, but only the values are going to be different. ऐसा कुछ है at t equal to 0. You can see that this value will be 0, this will be 5, because this peak is 10. This is minus 10. Now you can see that we can calibrate this very fast now, because क्या कॉन्सेप्ट यूज करेंगे हम यहाँ पे? देखो यहाँ पे थीटा का वैल्यू क्या था, पाई बाई 3. थीटा वाज पाई बाई 3 at that peak point. So theta is basically what? It is kx. So what should be the value of theta? So this is basically 2 pi by 6, 1/6 of this. So x should be equal to lambda by 6. X should be equal to lambda by 6. If your theta is 1/6 of a full cycle, 2 pi, then x should be equal to what? 1/6 of wavelength. And wavelength we had seen was 16 meters. So this point will become how much? This point is suppose x1. X1 will become 16 by 6, okay, or 8 by 3 meters. Why? Because let's understand, at that point, the value of kx1 plus phi should become how much? It should become pi by 2. Okay, so just substitute this and you'll understand why this happens. Just give me a second, guys. I'll restart the whiteboard software. So at this peak point, you can see that the value of kx plus phi should actually become pi by 2. So that is why you're getting the value of x1 as this, because kx1 plus pi by 6 should be equal to pi by 2. So your kx1 should be pi by 2 minus pi by 6, which is pi by 3. So 2 pi by lambda into x1 should be equal to pi by 3. So as you can see, x1 is lambda by 6. So the easy way to understand this is that this one. So if you look at this graph, ये वाले पॉइंट पे वैल्यू हाफ है, ये वाले पॉइंट पे वैल्यू 1 है. So if it's a theta kind of graph, this point and this point have a delta theta of how much? 90 degrees minus 30 degrees or 60 degrees, which is the same thing as 2 pi by 6, 1/6 of a circle. So now if you convert this into an x type of graph, okay, where this is y is equal to sin kx. So ये delta x कैसा होगा यहाँ पे? वापस if this is that half वाला point and this is that 1 वाला point, it should be such that k delta x should be equal to delta theta. Okay. So in other words, 2 pi by lambda into delta x should be equal to whatever that delta theta is. So if delta theta, for example, is 2 pi by 6, then accordingly my delta x will become how much? It will become lambda by 6. So this is the shortcut way of understanding this calculation. The x1 वहाँ पे lambda by 6 क्यों था? And lambda is nothing but 16 or 8 by 3 meters. This over here is the shortcut way of understanding that. Okay. Similarly, now you can see, suppose this point is x2. We'll understand very easily that x2 कितना हो जाएगा? It will be x1 plus lambda by 4. Because again, you look at this in terms of a sine graph. ये point पे phase कितना है? Pi by 2. और ये point पे phase कितना है? Pi. So the phase difference between these 2 points is pi by 2, which is 1/4 of 2 pi. So you can see that why this is the case is because you can see that kx1 plus phi, the phase at that point was how much? Pi by 2, whereas kx2 plus phi is how much? Pi. So the phase difference between these 2 points, just subtract these 2 equations. So k into x2 minus x1, that is the phase difference, is how much? Pi minus pi by 2, or that's pi by 2. So this is 2 pi by lambda into x2 minus x1. ये कितना है? It is 2 pi by 4. Pi by 2 is the same thing as this. Okay, so that means x2 minus x1 is 1/4 of a wavelength. So x2 should be equal to x1 plus lambda by 4. So that's why over here, this point x2 should become x1, which was 8 by 3, plus lambda, which is 16 by 4. So it should be 8 by 3 plus 4. So that will become 20 by 3. Yes. That will be the point x2. Okay, so this is something that you have to catch up on fast, on how to make the relationship between the phase difference between 2 points with respect to their coordinates x1 and x2. Okay, अगर 2 पॉइंट के coordinates x1 and x2 हैं, तो उनके बीच जो phase difference है, वो कितना हो जाएगा? k into x2 minus x1, or 2 pi by lambda into x2 minus x1. This becomes the phase difference between those 2 points. Phase difference means when we are applying the function e sine kx plus minus omega t plus phi, this whole thing is the phase. Okay, so at a point x1 it is kx1 plus some omega t plus phi. At a point x2 it is kx2 plus that same omega t plus phi. So phase difference जो दोनों के बीच है वो क्या है? It is just 2 pi by lambda into x2 minus x1. Okay. So relating that phase difference with the x2 minus x1, or the difference of coordinates of those 2 points, that is an important trick while solving these type of problems. Okay, so hope you've written this down. So that's the snapshot picture at p equal to 0. And in the snapshot picture, you can also see what these coordinates are. So for example, this point, this one is 8 by 3 meters. Okay, this one was 20 by 3 meters. So you can also understand the distance between these 2 points is coming out to be 20 by 3 minus 8 by 3. So that's 4 meters. That is in fact lambda by 4. So from this also you are seeing the justification that lambda is 60 meters. Okay. Now also one more thing you have to understand here is that this wave is traveling in this direction. So if I just look at its position after a very short time, t equal to delta t, this wave would have shifted and come like this. In that very short time delta t, the entire wave shape should have shifted by a small amount, delta x equal to v into delta t. But the interesting thing you will see here, which you will realize, is that you can also understand that at this point of time, the particle which is at the origin, where it is going downwards. So the particle velocity should be downwards. Okay. Whereas some other particle like this one is on its way up. This particle was also on its way down. So by just analyzing how the wave is shifting, you can also analyze which particles are going down, whereas which particles are going up at a given instant of time. Okay, so let's come to the last part of the question. So we've plotted the snapshot. Now let's find the particle velocity and acceleration at the point x equal to 4 meter at these 2 times. Okay. So that is again just applying mathematics, nothing else. This was our wave equation where E was 10 millimeters, K was 5 by 8 radians per meter, omega was 40 pi radians per second, and the phase constant phi was 5 by 6. Okay. Now let's understand particle velocity in general, del y by del t. So that is becoming minus E omega cos kx minus omega t plus phi, and particle acceleration del 2y by del t square. That is much easier here. Sin kx minus omega t plus phi. Why this sign remains minus is because cos ka derivative is negative, but there is a minus omega coming on. So it's a triple negative which becomes negative. So also one more thing you can see that the particle acceleration del 2y by del t square is minus omega square y. You compare this equation here with this equation, you can understand. So you can, that's clarifying the point that it's SHM with time period 2 pi by omega, which anyway you know. So anyway, now coming to this, the substitution. So at x equal to, what was it, 0, sorry, at x equal to 4, we had to find a t equal to 0. So at x equal to 4 meters, at t equal to 0, the particle velocity will become minus a omega cos of kx. So the k is pi by 8, so that's pi by 8 into 4 minus 0 plus pi by 6. So that is becoming minus 10 millimeters into omega, which is 40 pi. So this whole thing will be in millimeters per second into cos 90 minus 30. So that's sine 60. This is minus 400 pi sine pi by 3, or that is minus 200 pi root 3 millimeters per second. Minus sign is just showing you that it's on its way down. And similarly, if you substitute here, you get the particle acceleration as minus a omega square sine pi by 2 minus, oh sorry, this is cos plus, okay, so minus it, this is plus. So 90 plus 30 will give you minus sine 60, so this will become plus. Okay. So this is also plus. Now, sine 90 plus 30 will give you cos 60. So this will be minus a omega square cos 60 minus a omega square by 2. So the particle acceleration will have this kind of thing, minus 10 millimeter into 20 pi whole square by 2 in millimeters per second square. So just make a note of this. We wanted to find particle velocity and particle acceleration at this, at the point x equal to 4 meters at t equal to 0. Okay, people, so hope the calculation part and all is clear here. So with this, we complete the basic part of waves, which is the discussion about the harmonic wave. Now, next time we'll be seeing some more important things. For example, we will see that for the standard kind of simple harmonic wave, we already saw the relation V is equal to F lambda. But in this, we'll see significantly that the quantity wave speed, this is actually dependent on the string's physical state or physical properties, you can say. It does not depend on the source which is creating the waves. In fact, we'll see that it is square root of tension divided by linear mass density. This will be tension, mu will be mass per unit length. Okay. So it's completely dependent on the medium's properties. Okay. Whereas the quantity frequency, this is nothing but frequency of the source. Whatever is the source that is creating the disturbance, in this case a sinusoidal wave, that source is nothing but an oscillator which itself is oscillating with some frequency. So that frequency is nothing but the frequency of the wave, and accordingly lambda becomes the property of both source and medium. It is affected by both because the three are connected and one is dependent only on the medium, the velocity, whereas the other is dependent only on the source, that is the frequency. So the third property lambda, it kind of adjusts itself according to the properties of the medium and the source. So we'll look at that thing as something important in next lecture. And we'll also see the power propagated by a wave. Okay, the power propagated, which is basically the energy, the mechanical energy of oscillation propagated through the string per unit time. And we'll understand how this power comes out to be proportional to square of the amplitude in the case of the harmonic wave. So these are a couple of important things. We'll be looking at the derivation next time, and from there onwards we will continue more towards analysis of multiple waves and superposition and things like that. So now we are getting to a stage where you will have to do a serious read up of waves and revision of these two lectures, and also I'll send a set of some basic questions from HCB as well as the worksheet, the assignments that I've sent in bulk. So I'll just give you a list of some of the questions you can attempt before the next lecture. So just complete your test on Sunday, and after that get tracking on waves and make sure you do all this work before the next lecture. Okay, so all the best for the test coming up on Sunday, and do a proper revision of geometrical optics, particularly the last part, the combination of thin lenses in contact and lens in contact with mirror. Make sure to revise at least the questions we've done in class properly. Okay, and don't forget to go through the part about the chromatics or the dispersion of light due to prism and all those definitions of angular dispersion and this thing, dispersive power, and the combination of prisms, the achromatic combination and chromatic combination, those formula based kind of things and all. Make sure you go through those things, and also optical instruments including simple microscope, compound microscope, etc. Okay. So that's it. Thank you, people. Okay. All the best for the test once again.